Great to be here. My name is Dennis. Awesome to see so many people who came here for this session. Can you raise a hand if you have ever used the vector database? Okay, so like more than almost half of you. That's great. So we'll have a lot of fun today. And just to say, I live in Estonia, but I really like Warsaw. I like it apparently so much. I've been here 10 times only in the past year or so. So I have a lot of teams and colleagues here. So it's great to have an opportunity to come here to speak with you. What we're going to talk about? We'll talk about our largest vector search challenge at Bolt. I will share some of the brief, yeah? Oh, wait. Oh, it's such a small screen. Okay, I'll move here. Thank you. So yeah, we'll talk about our largest vector search challenge and a bit of like 101 into vector search of the internals there and paradox of choice. If you work with vector databases, I'm sure you struggled as well to figure out what to use and what's, compare with what's out there in the market and what you have inside, and our actual journey of using Redis at scale. I work at Bolt, and Bolt is quite a large company already. We have more than 200 million customers in 50 plus countries, and we have 100 plus ML models. There's a lot of data and machine learning, and all the challenges become more interesting and problematic at scale. And myself, I've worked at Bolt for more than 6 years. I joined as one of the earliest data platform engineers, and I was one of the first people who worked full-time on ML infrastructure. And now I'm happy to be leading our machine learning and experimentation platform teams, really great teams that help us to scale data and ML further. So how this whole journey of the vector search started? It was summer last year. I was meeting our stakeholders, and I was trying to probe. Vector databases, they're popular, right? There are some use cases. Do we have something? Do we need to plan for it? Do we need to do some research? And the answer was, no, we don't need anything. We are good. Nothing in the any near term. So of course, I was not surprised that 1 month later, there was an urgent business use case, high impact. We cannot hack it ticks anymore. We really need a vector database, and we need it now. The usual scale-up problems. And we try to avoid bringing complexity because we like to keep things simple. And of course, like Mr. Andrei Karpathy say, just use arrays, or like in this like Llama index, simple in memory storage works great. So let me explain why the hell did we actually, in the end, start to build vector database. So the use case for which we started to develop it was similarity search among users, which meant we need to have a vector for every single user we have on the platform. And also it meant that this is a collection that updates frequently. When the user changes some information about them or the new users are added, we need to update it, which is a key requirement, and you'll see why in the end. And of course, it should scale and be fast. Easy peasy, right? So we needed a proper solution. We just couldn't do it in memory because we want to keep our model services stateless. And if we need to do updates, well, it's not really a great idea across multiple replicas. So how many of you know how the vector search actually works? So I decide how fast to go here. Can you raise your hand if you know how it works, like the indexes there and so on? Actually, a lot. Then I'll just skip through it very quickly. You know the use cases, rugs, similarity search, semantic, let's just skip it. The super basic, you take some unstructured data, put it through embedding model, get some vectors so that they represent your data, and you can measure the distances between different vectors, right? Using Euclidean distance like we studied in school in geometry, or something more useful for your problem. And of course, you can build LLMs, rugs, find similar documents in your knowledge base, like from Confluence, and kind of get the real world context without having to fine tune the model. So we have vector storage, and we have a lot of vectors in our system. What helps us to query them efficiently? Can you help me? Did I hear? I heard a word. I think it was the right word. Index. Yeah, that's the right word. We need to have indexes. And of course, choosing them is like partially art, partially science. There are many things to consider, like dimensionality and whether you optimize for reads or for writes and how much data you're going to have. And the key thing about vector search that we always have to consider is, do we do exact nearest neighbor search? Do we try to find the exact top 100 documents? Or we are okay with approximate things? And from what I see right now is the HNSW, hierarchical navigatable small worlds, becoming the most popular if you need to get fast reads. It's like roughly a 9-year-old concept. And this is the one that our ML engineers have chosen in the end. Do you want to see how it actually works, or you know everything? Okay, okay. Roughly, you can think about it as like Google Maps. You know, if you're trying to figure out how to get somewhere to your destination, to this hotel in Warsaw, maybe you need to take a plane. So essentially, it's a graph index where you have several layers. The layer 0 will have all the nodes and all the connections like that you have. And each upper layer will have become more sparse and more sparse, which means the distances between nodes become larger. So you can think of and when you do a search, it's expensive index to build. It takes a lot of compute and time to rebuild this graph. And when you do changes, you need to make many changes. But idea is like this, like on Google Maps. You look at the highest level. So I need to fly from Tallinn to Warsaw. And what is the closest place to like this hotel room? Okay, that's to this hotel place. It's gonna be Warsaw on this higher level. So I go here, here's Warsaw. Let me go to this node like Warsaw Airport, get to the city level. To get from here, there are more nodes. For example, there are streets already and there are things like this. So let me find with a greedy approach the closest vector on this level. And for example, it's this hotel. And then we go to the actually very detailed level where we can do small tuning. Okay, we need to get to the second floor, to the room called whatever it's called. And this is the way we can kind of solve this vector search in like logarithmic time. So it's pretty cool index. That's what most people use. It's the most well supported. And this brings us to actually paradox of choice. How many vector databases do you know? 5, 10, 100, million, 3? Okay, 6. So this is one of the great websites that aggregates different vector databases. This small blue line is Redis. Why the hell did we pick it from here? The honest answer is we didn't pick it from here. But you can just see that the industry is growing like crazy. Everybody and their mother is adding support for vector search and vector indexes. And you will see many, many different benchmarks and things saying different things. So last year, we took a look at some of the top candidates like Milvus, Quadrant, Chroma. We had Elastic in the company. We considered that. And we were trading off. Should we try to bring something external or something internal? And of course, we read a bunch of articles. Redis claims to be the fastest. Like Milvus says that they have the best strategy and the best product, and Redis sucks. And Redis shows the benchmarks that they're 50 times faster than AWS OpenSearch and twice faster than somebody else, like have higher throughput. Try to figure out what is the real truth. So we had a fork in the road. Do we try to find the best possible global optimum for our future problems because we'll have many use cases for vector search? Or take something that's more or less well-known at Bolt and we have good support for? So this is the only meme I have in this presentation. Take a second to enjoy it. There's going to be no memes later. Every technical problem requires to understand the context of the company, organization, technology you already have. This is our context, very high-level view of ML platform at Bolt. When a client service, like a backend, needs to call to some model service, they don't talk to model because we like abstractions. We have a model invoker, which is essentially a gateway that abstracts away all ML deployed services, and it can provide monitoring, alerting, and some things like pull out additional features from the feature store without backend engineers having to think about it, full control to ML engineers and data scientists. And there's a model service that's deployed by our ML pipeline, and kind of ownership is split between like the client teams, ML platform team, and our users. So what we do have at Bolt for storage? What was our context technologically? We do have MySQL, doesn't have Redis vector support. TitaniumDB claims to have vector support in serverless, maybe in beta, whatever. Redis does have support with Redis search module. I didn't put on a slide, but we also have Elastic, but we had concerns with the performance of Elastic. So we were kind of pragmatic. We decided that we don't have time to onboard new technology. Site reliability team who will manage it and will have to be on call for it really, really don't like to add new technologies. So we had to respect them. So our idea was, let's prototype and benchmark Redis and abstract it away behind one of ML platform services. What it allows us is that if it sucks and if it's really horrible, we can just swap it out with something else with less pain for users. So why Redis? Well, except that we have expertise at running large-scale clusters, like sharded. It's not like just a single node. We have multiple nodes. And we have great monitoring, and it promises to be fast. It seemed like a kind of solid choice where we don't have to go and shop around and bring something completely new. And to integrate it within the ML platform, the logic is like this. we are a platform team. We want to solve problems in a reusable way. So that we solve this for this one large use case, but for the next use case, it should be much, much easier to onboard vector database without having to learn many things. Make sense? Makes sense. So we're roughly halfway there. Now it's going to be more specifically about Redis, and I will show you a little bit of code, how to run it. I'll show you benchmarks and the problems, of course, we've had on the journey to production. Here's an example. You can create an index. Here you put this HNSW. It has support for that. Amazing. You put some of the parameters for the graph construction, put your dimensionality, and key thing, Redis talks about, works on the prefixes. For example, it could be your collection, could be user, colon, and then user ID. Or whatever, product, something like this. So you put an index on a prefix. So every entry you insert with a key that has this prefix will be indexed. And to insert it, well, this is just like Redis thing. You just do like something called hset, kind of hash set. Put your key, put the some vector and some fields. You can put some other fields. Doesn't really matter for this problem. You can write this piece of code in like 20 lines of code and have a small benchmark yourself, which I do have on my laptop if you're curious to see that. And for search, we're doing k-nearest neighbor search. It's approximate search. You just put index name, this prefix we talked about, what is the k, how many vectors you want to find, and pretty much a couple of other details. That's it. Very simple. The complexity is not in this piece of code. One of the key things to understand about the benchmarks, what I really, really hate about all the benchmarks I see online, is they show you write performance, or they show you read performance, and I rarely, if ever, see how the reads perform if you have some number of writes. Redis is single-threaded, or almost, let's say, single-threaded, which essentially means you have writes and reads will compete for the same limited resource for the same event loop. And here's like 2 examples, just 2 points to show you. So for example, we take here 20 million vectors index, and we do no updates, P99 latency 2 milliseconds, CPU utilization 15%. Sounds amazing. Can't get much better than that. But if we do some writes, then P99 becomes 300 milliseconds, even though the CPU is like 19%. We decided that it looks pretty good enough. We can get 400 QPS with 300 millisecond P99 latency for about $1,000 a month in compute. It seemed like good enough for us to go for a prod. It looked similar to some of the alternatives we have seen, but it had proved performance. We have already production stuff for it, so we said let's go with it. And we did integrate it into those boxes I've shown you before. Now, ML pipeline doesn't only produce the model. It also essentially has a way to register like version or the index, your data set, dump with some library data to S3, in certain format your embeddings that ML pipeline produces, and our feature store takes care of the rest. So it ingests those vectors and makes them available for the queries. So now when the client team comes with a query that requires KNN search, it looks roughly like this. Client service will come, say, hey, give me this prediction, here are the properties, here's the input. Model invoker's like, hold on, let's go to the model, let's get embedding. The model will return, essentially there are some flags, and the model will return the vector. We will go to the feature store, find the nearest neighbors, using our Redis clusters, using these indexes, and then fully formed request with all this like vectors. So it's going to go for the model for the final, let's say, piece of logic, whatever it's going to do with it. And that's roughly the kind of whole architecture. So we made it fit more or less to our idea of model gateway and feature store and connected with the rest of the things. And it was pretty seamless. So how do you think? Did we succeed in production? Did we fail? Let's see. Of course, we had issues. And we had GitHub issues. Redis would hang for hours when trying to restore from a backup. And we had problems with latency when we started doing writes. And we had problems during the resharding. Luckily, Redis community is pretty responsive on GitHub issues, so we got to learn a lot about our knowledge gaps. Documentation isn't perfect. Some of the parameters that you have in the system are like the only place on the internet you can find them is on the GitHub in this conf.c file. That's the only place where you can read about them, nowhere else. No Stack Overflow, Perplexity will not know about it, so you have to actually read the code the old school way. But as we deployed it, this is how our reality looked like. You cannot maybe not see here, but like roughly the latency P99 was like about 20 milliseconds, pretty good. We had some spikes to 600 milliseconds. Not so great, but it was good enough for that use case. So we scaled it up. We added more users, we expanded it like geographically, and it was working. I would say it's like, I wouldn't call it a great success, but it's a moderate success. And here comes the kicker. I told you about one requirement. We need to do real-time updates to this index. This is one of the key features and key kind of problems why we, in the first place, went to do VectorDB. And also, I've shown you this graph index. Rebuilding this index is pretty heavy operation. It's pretty hard. So what do you think happened when we started to doing writes? It was slow. You know something about software. Yes, exactly. First of all, how did we add it? Pretty much we added one more box. So clients, we added one more endpoint. Client could talk to feature store, say, hey, here are the new properties, update embedding for it. We would go to the model, get embeddings, store them. Like pretty much there are just 2 API calls that were being added to the system, and now we have real-time updates. Pretty simple, final architecture, no more slides with the boxes. And this is how it looked. This is when we turned on the A/B test that adds writes. Doesn't look so good. And after that, we turn it off after a while. I have to say this problem is still half solved. Like we are still tweaking these things. We are trying to squeeze out what we can from this solution and negotiate also with our stakeholders what are the timeouts limits that are acceptable. But this is a learning. Like even though we did benchmark for it, something went wrong and things didn't go exactly as expected. Well, that's life. And generally we had like a bunch of other challenges. And in these final few minutes, I'll talk about the challenges and I'll talk about the bright future that we can see for the vector search in the industry. So we had problems with ingestion speed. We had problems because Redis search is not part of the core Redis yet. So we had to compile module from a branch to have some new functionality and parameters available that are not released yet. We had to create logical sharding because when the index grew more than 20 million, things didn't perform. And if you'll see most of the benchmarks, it show you like 20 million index size benchmarks. Redis has a 1 billion vector benchmark, but most of them are around 20 million. And of course, latency degraded. But generally, setup is like good enough to run in production for our use case. So we can horizontally scale it. We can add more nodes, wait a bit, data will get resharded, which is great. That's really nice. Generally, search is fast, unless you overload the Redis with writes. Fits in our stack, okay, costs. It's not the best possible thing in the world, in my opinion, but it worked. And future, I think, is actually bright. The industry evolves so quickly. Like was said by the previous presenters, what was true yesterday might not be true today. We'll be able to make it simpler for the users and more integrated now that we have learned and created this kind of pipeline. And Redis 8, like in many of the GitHub issues, they told us, we have implemented it in Redis 8, please wait for it. And ETA for Redis 8 was sometime this year. So we don't know if we'll survive, if we can scale further, or we're gonna crash. But what was surprising is that actually yesterday, release candidate 1 popped up from Redis. So we've been waiting for it for months, and we had a lot of promises. So of course, what I had to do, I had to benchmark it. Not very scientific test on my laptop on 5 million index with having 300 QPS, 100 writes per second and 200 reads per second. We get to have about 22 millisecond P95 latency. And P50 is even 4 milliseconds. To be honest, some of the benchmarks were unstable, probably more related to my laptop. But in the best case scenario, it might work. And also, I've looked at the parameters that are exposed in Redis 8. There is so much more config parameters. So it's possible that we will get, I'll fly back to Estonia. My team will do more tweaks. And in a couple of weeks, we'll have next talk ready with how we solve this problem you've seen in the chart before. So the takeaways, most likely, most of you've tried it. I would guess you have taken something you already have, or you prototype some other database. But in many cases, unless you have really high scale or really specific requirements, you can try to get by with existing tech. If you have Postgres and you have pgvector, probably you're lucky and maybe your life is simple. We have MySQL in the company, so our life was not simple. And that's why I would say probably argue, don't build maybe too much dependencies on a specific vector database solution. Like don't go for the craziest index unless you have a really good reason. Because field changes, new players will come and go, and you might need to swap it out later. That's all I have for now. Thank you very much, and I would be happy to talk to you later. Thank you so much.